About a month ago, I made a video trying to calculate how often the new Leyline deck could win on turn 2. And a lot of people had questions about that deck that I couldn't answer with the janky Python code that I wrote. So I started writing some more robust code, and lo and behold, the deck got banned in Best of 1 Arena while I was working. Without Leyline, the deck can obviously no longer win on turn 2, but I want to know exactly how much slower the ban made the deck. Conveniently, the code I wrote is designed to answer exactly those sorts of questions. It basically functions as a goldfishing simulator. Goldfishing is the act of playing a magic deck against an imaginary opponent that does nothing to stop you. There are obvious limitations to this kind of analysis, but for an all-in aggro deck, I think measuring the speed at which a deck wins in this scenario is pretty useful, so I set out to build a system that could simulate many rounds of goldfishing at once. To get started, we need to define the concept of a game state. A game state is basically a snapshot of a game at a certain moment in time. It contains information about your opponent's life total, your hand, your deck, your lands, your creatures, and your other permanents. Given a particular game state, we can take game actions that produce new game states. For example, we could play out a card from our hand, move to attacks, or pass the turn. Our goal then is to use these transformations to find a game state that puts our opponent's life total to 0 in the minimum number of turns. This leaves us with two problems. At a given point in our search, how will we know if we've missed a possible win? And given that we found a win, how will we know that it is as fast as possible? To solve these problems, we'll use a hash set. It's okay if you don't know what this is, just know that it allows us to take something, in this case a string denoting a certain game state, and quickly tells us if it's in our set or not. With this, we can keep track of all of the states we've seen before. In addition to the hash set, we also need to keep track of the states we still need to evaluate, which we'll call the frontier. Now our search starts like this. We begin with our initial state and place it in our frontier. Next we start our loop where we begin by taking a state off of our frontier. First, we check to see if our state has already been seen. If so, we move on immediately. However, if it hasn't been seen, we use our transformations to get every state reachable from our current state, with one exception. We'll not be ending the turn yet. We then take our current state and add it to the hash set, as well as adding all of our new states back to the frontier. We continue this loop until this frontier is empty. That means we've seen all the possible states that we could see without ending the turn. To move to the next turn, we start by taking all of the states out of our hash set. Then we transform them all with an untap, upkeep, and draw. Then we can remove all of our states and put them back on the frontier, starting the process all over again. At every stage in this process, we check to see if the states we are mutating has already won. And since we've seen every possible game state of the turn we just finished, we know that we're guaranteed to find a win as soon as one presents itself. However, as you can probably see, the number of states we have to process grows exponentially for each turn the game goes on. However, games typically finish quickly enough that we can get our answer before our game states balloon completely out of control. I also do a few things to prune away game states that I know are suboptimal, so our set never gets so big that it can't fit on my computer, which is pretty convenient. Using this process, I tested 5 different decks. On the left you see the core of the deck, which didn't change over the course of the experiments. Of course, I started by adding Leyline. This is the most popular configuration before the banning. Then I removed Leyline. I didn't add any substitutions at first. This is an illegal magic deck because it doesn't contain 60 cards, but I just wanted to see what would happen if you didn't add any substitutions. I then tested the deck with 3 different substitutions: Dreadma's Ire, Eberhard Challenger, and Lightning Strike, which I considered reasonable substitutions. Okay, here are the results. The vertical axis is the number of games out of 10,000 that finished on a given turn, which is on the x-axis. So as you can see, obviously removing Leyline removes any possibility of a turn 2 kill, but some of these other numbers are actually pretty interesting. For example, turn 5, there's kind of like a downward slope as we add different kinds of substitutions, other than Ember Heart Challenger. It seems like Ember Heart Challenger kind of slows the deck down overall, but maybe it makes it more resilient, so who knows if it's a good choice. But as we add more substitutions, these kind of terrible results, like turn 5, turn 6, turn 7, kind of go down. You can see Lightning Strike is pretty consistent, but it gets mostly turn 4 wins, as opposed to turn 3 wins. It gets kind of fewer of those. So it seems like removing Leyline doesn't really make the deck slower on average, it just makes it more consistent, more closely huddled around this turn 4 win, which I think is generally healthier. You can see Lightning Strike actually has the lowest average overall, so it's technically faster than Leyline on average. You just don't get any of those freakish turn 2, turn 3 kills as often. You still do get some. But yeah, I think this is kind of healthy for the format in general. Best of 3 can kind of handle this kind of variance more than best of 1. You all get the one game in best of 1. So I think kind of narrowing the variance of when you're likely to get killed is kind of helpful. So now you can kind of expect, hey, I need something by turn 3, turn 4, or I'm going to die. As opposed to, I need something on turn 1 or I'm going to die. I will be publishing this code on GitHub, and I might make a video going over it if there's an appetite to do that. It's kind of a lot more serious than the last code. I wrote it in Java, which is a language I'm more comfortable in. There's different classes. I even wrote some unit tests. But yeah, so I would imagine it would be pretty boring for most people to go through the code. But there's some interesting design decisions and optimizations to make it go a little faster. Yeah, but the good thing about this code is it's pretty extensible. Like I can make new spells and test new kinds of decks. So if anyone has a question about like an aggro deck or a combo deck in the comment that it might be useful to Goldfish, yeah, just leave it in the comments and I might get to it if I think it's interesting. But yeah, other than that, that's the end of the video. So cheers.